Welcome to CS471. So in today's lecture, we're going to talk about RAID, redundant array of inexpensive disks. Recall that in the previous lectures, we've talked about the fundamentals about I/O devices and hard disk drive, HDDs, right? So HDDs have these inherent properties of, you know, slow performance because it's just a piece of mechanical hardware. It consists of a different piece of mechanical parts just for facilitating supporting I/O operations. So the very first property of a single hard disk drive is, a single disk is very slow. It's kind of good for sequential I/O performance if the I/O is touching a consecutive set of sectors or disk blocks. But hard disk drive, mechanical spinning hard disk drive is extremely bad at, random I/O because random I/O, many concurrent random small I/Os will make the device quite busy just moving its disk arm back and forth just for locating the small sector blocks spread across a huge range within the address space of the hard disk drive. So basically, the very first property is, a hard disk drive is quite slow. So, and because we're always talking about a single hard disk drive, with that, we know it always have, a limited storage capacity. So this is the second inherent property of single disk. Its storage capacity is kind of limited. If you have a large volume of data that you want to store, if that capacity exceeds the storage capacity limit of a single storage disk, you may want to think of a better option for accommodating this storage requirement. So the third property is the reliability. So what is the definition of reliability? So it's the property that used to describe the capability of tolerating any potential hardware or software failures. So if we're talking about a single disk, if that single disk dies down, so the reliability cannot be guaranteed. The reliability of your data cannot be guaranteed, right? So all these three inherent not so good properties of a single hard disk drive motivates a better system design, which is the major topic that we're going to discuss today, which is RAID, redundant array of inexpensive disks. Okay. So again, with those three not so good properties, inherent properties of a single hard disk drive, so we do have a wish list for a single hard disk drive, right? So first of all, performance. We don't always want we do always want the performance to be good, right? Especially for the I/O part, because I/O part is always the bottleneck. So we want a storage system to be performing relatively faster. This is the first wish of this wish list. And as the second wish list, we do want a hard disk drive to be having larger capacity. The more, the better, right? Because right now we're talking about like big data. More and more data needs to be stored. This is the capacity requirement. And we do have a third requirement. So given that we have more and more data that needs to be stored, we also want these massive volume data to be stored in a reliable fashion, right? So we wish them to be stored more reliably. and we don't want our valuable data to be corrupted, to be lost due to either software-based failure or hardware-based failure, right? So whenever we're talking about hardware, not a single piece of hardware is perfect. It do suffer from like this and that hardware-based uh, issues, and some of the issues might be critical, and that might just bring down this device, and we may be facing with the risk of permanently losing the data stored within that device. So we really want this reliability property, right? So with only one single disk, we cannot kind of fulfill all these three properties simultaneously. And the great challenge lies in that most, if not all, file systems they work on only one single disk. So by assumption, by default, they assume the underlying storage hardware it consists of only one single device, right? However, with only one single device, we cannot fulfill the performance requirement, the capacity requirement, as well as the more important reliability requirement. So this to motivate a better software-based solution, which is called redundant array of inexpensive disks, right? So at its core, the the fundamental idea of RAID is to just comprehensively and cohesively combine multiple physical hard disk drive together and expose a unified interface, unified and transparent interface to this um, upper level applications and file systems. So here within this within this example, we have a layered uh, system architecture where the topmost layer is application, right? And then application directly interact with file system for and the file system is a core piece of software system that is used to arbitrate and support read and write operations. And the file system itself is responsible for directly interacting with the low-level device driver as well as the hardware for performing read and write I/O operations. And underneath the file system layer, we could kind of treat this RAID-based logical disk as a single piece of unit. Okay, so this single piece of unit logically combines multiple disk drives and expose a unified interface to these upper level applications, for example, file system. From the RAID perspective, file system is also one of its applications. Okay, so the the ultimate objective of RAID is to provide, first of all, transparency, and then ease of deployment property to the upper level applications. So you might be wondering, what is transparency? Well, transparency means, the upper level applications, in this case, file system, is kind of not aware of this existence of such an extra logical layer, which is, this RAID logical disk layer, right? So the file system, the RAID logical disk layer behaves as if it exposes a unified interface to this upper level application. So this is transparency. And file system is not fully aware of its existence. So the next property that will be achieved by RAID is this ease of deployment, this second property. So what is ease of deployment? Well, by deployable, I mean the RAID could be seamlessly integrated into this system, this whole system IO stack, without a need to, without a requirement for the developers to make any significant software level modifications, or without the requirement for hardware engineers to make any significant hardware based modification just in order to accommodate this newly introduced logical layer, right? So this is typically ease of deployment. It's just like hot plug in. You can just pretty much hot plug in a RAID layer into the system, and it will just automatically and transparently provide this the functionality as if this application, this user level application, as well as this system level file system, it itself thinks, oh, it's only talking with the default hard disk drive, right? So this is there's two objectives that are targeted by RAID. And also, the logical disks, RAID, it inherently enables better performance because it cohesively combines multiple disks. So naturally, the performance will be doubled or tripled, right? Depending on how many disks are utilized by this RAID layer. So this is a performance. And the second benefit is it enables larger capacity. Now, this is also understandable, right? Because by using multiple hard disk drives, you're basically looking at a larger capacity, combined larger capacity, and also reliability. Well, so because you have larger capacity, that means you could be able to store your data with multiple copies. If you spread your multiple copies of exactly the same piece of data across different hard disk drives, it inherently guarantees better, it inherently enables better reliability, as shown in this next slide. So in this example, we have two unique pieces of data, block A and block B. And each one of these data blocks gets replicated twice. So basically, we could say the replication factor of each and every block within the system is 2. Replication factor is equal to 2 in this case. So according to its replication and data placement policy, in this specific case, block A gets duplicated in the first disk and the second disk, whereas block B duplicated in the first disk and the third disk. So by duplicating these data multiple times, it inherently enhances the reliability properties, right? If let's say one disk, let's say the first disk goes down, let's say due to hardware failure, we still have data availability because we maintain one extra data copy in disk 2 and disk 3, right? All right, so you might be wondering why we want to design such a logical, redundant array of inexpensive disks that combines multiple very cheap hard disk drives. Well, the major motivation of doing this is to exploit this cheap property of multiple inexpensive disks because you can just get many commodity hardware components with the same price as a few expensive components, right? Economics of scale. Basically, you get more devices. With more devices, that means you get more capacity. You get more capacity with better performance. And also, the larger capacity, it also directly corresponds to better reliability. Okay. And the key enabler of the RAID methodology is, we could use software technology to synergistically combine multiple really inexpensive, cheap hardware devices, to be able to build provide high quality services to the upper level applications, for example, file systems. And here there's inherent trade-off. And this trade-off is to compensate the poor properties of the cheap devices in order to achieve better performance, better capacity, and better reliability. So the core idea of redundant array of inexpensive disks is to combine multiple disks together. In its simplest example, as shown in this slide, we have two hard disk drives. In this case, we have disk 1 and disk 2. And here, on top of these two disks, we build a logical software layer which combines these two disks together and exposes a unified, larger address space, ranging from address 0 all the way to address 200 to the applications. And this strategy is called striping, which will be talked about in the next couple of slides. All right, so in order to improve the reliability, we could add some replication support to replicate the data multiple times so as to provide better reliability. And in this particular example, we have disk 1, disk 2, disk 3, and disk 4. We have a total number of 4 disks. And on top of these 4 disks, we build a single RAID layer which exposes a unified address space of 200 sectors, ranging from sector 0 all the way to sector 200. And it supports a replication factor of 2, right? Because each piece of data is duplicated twice. The first half of the address space, ranging from 0 to 100. This first half of the data gets duplicated both on disk 1 and disk 2. And the second half of this address space gets duplicated on the second set of these 4 hard disk drives, gets duplicated on disk 3 and disk 4. So basically, by adding more number of disks, you get reliability plus plus, right? So whenever we're talking about new technology, one of the most important consideration is the metrics that is considered, that is touched by this new technology. And the same for RAID. So when talking about RAID, in the context of RAID, we're looking at these three basic metrics. The first one is, performance, like the sequential bandwidth, especially for large sequential base I/O, and the random uh, latencies for the random I/Os. So these two are basically in the context of performance of enabled by the RAID technology. And the second metric is capacity. Like how many space can each application use for a specific RAID configuration. And the third is reliability, especially uh, like how many disks can the application safely lose in terms of reliability. So these three different kind of um, matrix, multiple dimensional matrix. And here, especially for reliability, here we assume a fail-stop model where each disk can only have two different states. The two states. The fail-stop model. The first state is the working state, and the second state is the failure state. So while this is a relatively simplified failure model, it does capture a whole lot of application scenarios, potential corner cases that will be discussed when talking about like the different RAID configurations in the next couple of slides. Okay. So next, we'll move on to talk about different RAID configurations. So in today's lecture, so in the context of CS471, we are only interested in RAID 0, RAID 1, RAID 4, and RAID 5. These four different levels. Because these four configurations are the most commonly used approaches by commodity servers. So let's first zoom into the first level, which is RAID 0, which is non-redundant striping. So RAID 0 is also called striping. Striping means you just chop up the data into the granularity, multiple logical blocks, and you stripe these logical blocks among different devices. As shown in this particular example at the bottom half of this slide, we have a total number of 6 blocks, right? And if we want to use striping, a relatively straightforward striping strategy is to map the half of it into disk 0 and the second half of it into disk 1, basically rotating. Block 0 gets mapped to disk 1, block 1 gets mapped to disk block 0 gets mapped to the first disk, which is disk 0, and block 1 gets mapped to the second disk, which is disk 1, right? And you basically rotate the orders with this strategy. So the first level, RAID 0, it basically serves as an upper bound. It serves as the best case scenario in terms of performance and capacity. And the reason why is because we don't ever consider replication in this case. And it also fully utilizes the performance benefit of multiple hard disk drives, right? So in terms of both performance and capacity, it serves as the theoretical upper bound when comparing to other different RAID configurations. For example, RAID 1, RAID 4, and the last one that we'll be talking about, RAID 5. So Here in this slide, it shows a very simple example of a 4-disk RAID 0 composition. It's basically a two-dimensional table, and the column-wise, it shows different hard disks. We have a disk 0 all the way to disk 3, and this is column-wise. And on the second dimension, row-wise, we have different offset. This is offset. And within each and every hard disk drive, let's say hard disk drive 0, it has a total number of 4 offset. Offset 0, 1, 2, 3. And this is the row-wise. And this is a typical example of striping. And here, a row in this particular example is called a stripe. So a question naturally arises is how to calculate the stripe number and how to calculate where exactly an address falls into which specific disk as well as which specific offset within a particular disk. Well, so let's say given logical address A, in order to calculate its disk number and offset number, we could just pretty much rely on these two formulas. So the disk number where address A lies in is equal to A modular the disk count. And in order to calculate offset within a specific disk, you could just use A divided by the total number of disks involved in this specific RAID 0 configuration, right? If you take a look at this example, you want to calculate the disk number as well as the offset value for a logical address 1313. So a 13 modular 4 gives you 1. It means, well, disk address 13 lies in the second disk, which is disk number 1. And to calculate the offset, 13 divided by 4 gives you 3. It means it is the fourth logical block that is stored within disk 1 because it has an offset of 3. So this is the location where this particular provided logical address 13 is stored within this RAID 0 configuration. All right. So typically, in its simplest form, we assume a chunk size of 1, as shown in this particular example on the top half of this slide. In some other cases, we can also configure a system to use variable chunk sizes, which is configurable. And as shown in this example at the bottom half of this slide, we have a configurable, we configure the chunk size to be 2, right? If the chunk size to be 2, basically that means these 2 consecutive offset within a single disk. It corresponds to a single logical RAID chunk. Okay, but for the simplicity in the following examples, we basically assume a chunk size of 1. So next, let's perform some theoretical analysis to kind of quantify the theoretical values that can be achieved by each of the 3 major metrics, namely capacity metric, reliability metric. This is the capacity and reliability metric and performance metric. Okay, so in terms of, especially in terms of performance, we're basically looking at these 2 different categories. The first one is throughput. And throughput is especially for like relatively sequential oriented I/O. And for latency, this is especially for random small I/Os. Okay. So, so this is the theoretical results of each one of these metrics of interest for RAID 0. So a bit more about the background of these constants. So here we assume n is the total number of hard disk drives we have included in this RAID 0. So this is n. So what is C? C is basically the capacity of a single disk. And here we assume a homogeneous configuration across all the disks, which means that each and every disk has exactly the same capacity. Same capacity. So this is C. So moving on to the performance, we have three more letters. So what does S mean? S means the sequential throughput, while R means a random throughput. Okay, and here D, whenever talking about latency, we have this metric which is called D. And D is just the latency for a single small random I/O. All right. So this is the definition of these constants, these macros. So let's next take a look at let's next go through each one of these metrics of interest for providing a theoretical analysis of this RAID 0 configuration. So first of all, why its capacity is n times C? Well, this is relatively straightforward, right? Because if assume we have a total number of 4 hard disk drives, and especially for RAID 0, it's striping. It doesn't incur any replication overhead. It doesn't try to duplicate the data multiple times, meaning each and every piece of logical block is only stored single time, only once. So that achieves a theoretical upper bound in terms of capacity. So let's say we have a total number of 4 disks. It's basically 4 times C, assuming the C is the capacity of each one of these hard disk drives. So this is the capacity. Moving on to the reliability analysis. How many disks can fail? How many? Well, the answer is 0, right? Because we don't provide any reliability guarantee because the same piece of data is stored only once. So whenever one single disk fails, it means we basically lose the portion of the data stored therein. So this is the reliability consideration. Moving on to throughput. Well, for throughput, it basically achieves the maximum as well. Let's again take a look at this 4 disk based RAID 0. Well, let's say sequential I/O. What is sequential I/O? Sequential I/O basically scanning a large portion of consecutive logical addresses. So it first scanned the very first disk, and then scanned the second disk, the third disk, and the fourth disk, right? And all this sequential scan can happen simultaneously, concurrently, which means it doubles the performance if we have only 2 disks. It triples the performance if we have only 3 disks. If we have 4 disks, the performance improvement metric, the scalability, the speed up would be 4, right? In this case. So it would be 4 times S if S is equal to the sequential throughput that could be achieved by a single hard disk drive. So this is a sequential performance. For random I/O, basically, we can use exactly the same theory, right? Because we have 4 disks deployed. So the random throughput is basically the aggregated sum of the throughput that could be achieved by these 4 disks simultaneously together. So that is why we have the random aggregated throughput, which is n times r. Both of these two factors, they have a speed up factor of 4 in this case, and for a more general case, a speed up of n, right? Assuming we have a total number of n hard disk drives employed by this RAID 0. And for latency, well, why we have a latency of d? So this has to do with the random I/O. So what is random I/O? Random I/O is at a single point of time, we have a random I/O hitting here, and maybe at the same point of time we have a random I/O hitting here, here as well, and somewhere over here on disk 3, right? But the latency wise, it basically is equal to the exact same latency as is observed by a single hard disk drive. So it takes the same amount of time just for this particular random I/O to get responded, which is basically D, right? For each and every one of these hard disk drives, it will spend at least this amount of time, which is D millisecond, let's say, just to finish serving this particular small I/O. So regarding the random I/O latency, is D. And this is for RAID 0. So let's move on to the second RAID configuration, RAID 1, which is also called mirroring. So the core idea of RAID 1 is to keep 2 copies of exactly the same data. Basically have a replication factor of 2, right? So here in this example shown in this slide, we have a total number of 4 logical blocks, and this layer representing this logical RAID layer, and the second layer underneath it, this layer, this is a physical layer, physical hard disk drive layer. Okay, and here this physical hard disk drive layer, it spans like 2 disks. So for the same amount of data, it gets duplicated twice. It gets first stored on it with a full set on disk 0, and then gets a mirrored image on disk 1. So this is why it's also called mirroring. So this is the core idea, high-level idea of RAID 1. So again, we basically assume a failure model, which is called fail-stop, where I'll just exactly look at 2 different states, as we've already discussed in the previous slides. They either work or they don't. This is a failure. They work or they fail. So, and another assumption is we just know that when they don't work. So this is just for simplicity of better illustration to better understand this high level design principle as part of this operating system. Okay, so next I'm going to use these examples to better illustrate how exactly RAID number one works. So here in this example, again we assume we have a total number of 4 disks, ranging from disk number 0 all the way to disk number 3. And here the exact same piece of data gets duplicated twice. So the logical block number 0 gets duplicated on both disk 0 and disk 1. And the same for the rest of those logical blocks. Here we have a total number of 8 logical blocks, ranging from logical block 0 all the way to logic block 7. And logical block 7 gets duplicated on the second set of the disks, disk 2 and disk 3, right? So 7 gets duplicated on these 2 devices. So the next question is, how many disks can fail? Or if we ask this question a different way, what is a reliability? What is a quantified reliability that could be inherently enabled by RAID 1, right? So here, basically, the answer depends. It could be either 1 or 2. Why depends? Because it depends on which exact disk fails. Let's say if both disk 0 and disk 1 fails, so that means we basically lose half of the data, which is not good, right? So for this particular case, we cannot tolerate the 2 disks failure where these 2 disks store exactly the same data. So that is why, if for this particular case, we can only, like stochastically, we can only tolerate a single disk failure. But in some cases, if we're lucky enough, we could just tolerate 2 hard disk failures. If instead disk 0 and disk 3, the first disk and last disk, they get failed. And this is fine because we still have its replicated data stored on disk 1 and disk 2. So in this example, we can tolerate exact 2 disk failures. So that is the reason why this reliability model, it gives 2 possible answers, 1 or 2. It depends on which exact disk fail, right? So let's move on to the theoretical analysis of RAID 1. So first of all, what is a capacity? Well, since, it duplicates data twice, so basically we lose half of its, we effectively lose half of its capacity for storing more data. So that is why it has a like decreasing factor of 2. That is why we divide it by 2, which is basically n times c divided by 2. So this is a capacity metric. And obviously this is smaller than, it's only half of the theoretical upper bound, which is naturally enabled by RAID number 0. In RAID 0, the capacity metric has a value of n times c, right? So this is a theoretical upper bound. Okay, so this is capacity. And the next, let's see reliability. Like we've already discussed in the previous slide, reliability is 1 or maybe n divided by 2. In the previous case where n is 4, right? So it's 4 divided by 2 gives you 2. And why we have this maybe keyword over here is because it pretty much depends on which exact set of hard disk drive fails. If unfortunately we get the set of disks that are used to store the whole set of data failed, and then we basically lose half of the data, which is not fine, right? So this is reliability. And next, we take a look at the throughput metric. So we have a total number of 4 factors, 4 metrics under throughput metric: sequential read, sequential write, random read, and random write. And each of these 4 factors, they have a performance number, theoretical performance value, right? So let's first take a look at sequential read and sequential write. So sequential read and sequential write, this is a kind of trivial, right? Because the thing we kind of so let's say we have a total number of 4 disks: disk 0, disk 1, disk 2, and disk 3. And we have the data duplicated into the first 2 disks and the second 2 disks. So basically we have 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, something like that, right? So regarding sequential read, basically we're looking at n times 3, n times s divided by 2. Why we have a decreasing factor of 2 is because in order to sequentially read a large chunk of data, we can only leverage half of these 4 disks. In this particular example, right, it is, we basically want to read 0 first, and then we want to read 1. And here we want to read 2 over here. And then we want to read 3 over here. And then followed by 4 and 5. As you can see, even though, like at first glance, we fully leverage this total number of 4 disks together in order to simultaneously support this sequential read, sequential large read. But if you zoom into one single disk, let's say we pick disk 0 over here, and this is disk 0. And in fact, what exactly happening inside of disk 0 is, it is kind of rotating. It's skipping one block and directly jump to the next block over here, from 0 all the way to 4. And then from 4, you skip another thing and jump to a different one, which is another block. So in theory, you are not fully utilizing the whole sequential bandwidth that is inherently enabled by this single hard disk drive, but instead you only leverage half of it. So that is why we have a decreasing factor of 2 here. And the same for sequential write, because you are doing this write in a rotation manner. You write over here, and then you write over here, you write over here, you write over here. Even though logically speaking, this is a sequential write, but in fact, from the perspective of single hard disk drive, you are skipping one block and write to the next block, and you are skipping another one next, and then write to the next. You are not fully utilizing this whole sequential write bandwidth, but you could only effectively utilize half of it. So that is why you need to divide this n times s divided by 2 to give you this effective sequential read and write bandwidth. Okay? So this is the sequential read and write. So in terms of random read, you have a scalability factor of R without a decreasing factor of 2, because again we use the same example. We have total number of 4 disks, right? And for random write, stochastically speaking, and this random, if we have a relatively fair large amount of concurrent simultaneous random read requests, that would be spread across evenly across all these 4 hard disk drives, right? No matter whether it's hitting on the original data or it's duplicate. Let's say this one stores 0, This one stores 0 again. 1, 1, 2, 2, 3, 3. So no matter whether the target result is 0, this 0, or that 0, basically it can fully utilize this whole bandwidth provided by these 4 hard disk drives. So that is why we're looking at n times r. So this is for random read. For random write, and basically we're looking at the same thing. So just refer to the theory of how we get sequential read and sequential write, because we also need to apply a decreasing factor of 2 over here. Because of this rotating write, you have to skip one more just to write to the next one, right? And for latency, it's D, for small random I/O latency. Right? This is D, and it's the same for both random read and the random write. It's both D. All right, so let's move on to RAID 4. So here, we're looking at this two-dimensional matrix space. So at the horizontal dimension, we have capacity, and the vertical dimension, we have reliability. Like we've already discussed two basic RAID configurations. We have RAID 0 and RAID 1. So like we've already talked about, RAID 0 serves as the theoretical upper bound in terms of both performance and capacity. So that is why it lies over here, because it has the highest capacity metric. But regarding reliability, it has the worst reliability, because it cannot tolerate at a single disk failure. So that is why it has a relatively lower reliability as compared to RAID 1. RAID 1, on the other hand, it improves the reliability as compared to RAID 0. But at the same time, it effectively sacrifices half of its aggregated disk space in order to gain better reliability, because it uses mirroring. It supports a replication factor of 2, meaning each data gets replicated twice, right? So it has a capacity which is smaller than RAID 0. And then we introduce the next configuration, which is called RAID 4, which basically tries to combine the best of both worlds. This is where roughly a RAID 4 lies in. It tries to achieve good enough capacity, approaching what could be achieved by a RAID 1. And at the same time, it's tried to achieve good enough reliability, approaching a level that could ever be achieved by RAID 1, right? At most tolerate one single disk failure, or maybe 2 disk failures. It tries to combine the best of both worlds by using an approach which is called parity disk. So what is parity? Well, in algebra, if an equation has exact n variables and n minus 1 are known, and then you can use this already known n minus 1 variables to calculate the only one left that is unknown. And this is a core idea that is leveraged by this parity disk strategy adopted by RAID 4 in order to achieve this combined effect of good reliability together with good performance and good capacity. And the high level strategy is to treat the sectors, treat the stripes of blocks as an equation, and use the n-1 known factors to calculate the ones that has been lost, right? So as to provide the fault tolerance support inherently. And a failed disk is just like an unknown, right, in that equation. All right, so here's the logical layout of a simple example. In this example, we have a total number of 5 disks from disk number 0 all the way to disk number 4. And here, this disk 4 is called parity disk. And this is solely used for, this particular parity disk is solely used for storing parity chunks. And where the first 4 disks, disk 1, disk 0, disk 1, disk 2, and disk 3, they are used to store data chunks. Okay. And here, let's say here's a stripe, and this is the data chunks 4, 3, 0, and 2. The disk 0 stores a logical chunk 4, and here the result of, in order to calculate the parity that is stored at the parity disk, which is disk number 4, you need, for example, you need to just to use this linear algebra kind of operation. 4 plus 3 plus 0 plus 2 gives you 9, which means the parity value is 9 over here, right? Okay. So let's say at some point of time, this data, the logical data block stored in disk number 0 gets lost. So in order to recover it, you could just apply the same linear algebra operation by doing this subtraction. 9 divided by 9 subtract 3 subtract 0 subtract 2. This is a parity. And this gives you 4, right? So using this parity combined approach, you could just effectively recover the disk failure, a single disk failure. That also means that you can tolerate single disk failure over here, right? With that, the already lost data block that's stored within disk 0 is 4. Okay? In real world cases, a real world RAID often uses this exclusive OR operations to support this parity calculation. Here in this example, if we have the total number of 1 in a stripe, if the total number of 1 in a stripe is an even number, you get a parity value of 0. But if, on the other hand, the total number of 1s in a stripe is an odd number, you get a parity value of 1. So if you take a look at this modified example using exclusive OR as the calculator, so this is how it looks like within a single stripe, right? So the high bits, it has a total number of, if you take a look at the high bits, the first bit. For this particular example, it has a total number of 3 ones. So that gives you the parity of 1. And then if you take a look at the low bits, 0, 0, 1, 0, it has only one single 1. So that gives you a parity of 1 because both of these 3 ones and 1 ones, they are both odd number. So that determines the parity of 1, 1, right? And you can do the same calculation for the stripe underneath, which you end up having a parity result of 1, 0. So let's say at a certain point of time, again, the first logical block gets lost because the first disk 0 gets failed, right? You can just apply the same exclusive OR calculation to get the lost data chunk. So how to do it is by just applying this exclusive OR operation on top of it, and you just count the total number of ones for each and every bit. In this case, we have 2 bits, right? So for the high bits, we have 1, 1, 1, 1. We have 4 ones, which gives you 0. And if you do the low bits, we have a total number of 2 ones, which again gives you 0. So that is why we end up with this exclusive OR result of 0, 0. So that means this last thing is 0, 0 previously. So that is why how we could effectively recover the lost data block, which is block number 0. Okay, so let's move on to this theoretical analysis of RAID 4. So first of all, what is a capacity? Well, since we have a total number of n disks, out of this n, only one single disk is solely designated for storing parity chunks, right? So effectively, we have the rest n minus 1 times c for storing effective data instead of parity. So that's why we have n minus 1 times c for capacity. Like how many disks can fail? In the previous example, because we use only one single parity disk for storing parity chunks, that means we could tolerate as many as only one single disk failure. It cannot tolerate more than one single disk failure because this parity calculation won't be able to recover the lost data if there are 2 disk failures simultaneously, right? So that's why we have a single. It can only tolerate one single disk failure. So this is reliability of that could be achieved by this default off-the-shelf RAID 4. Regarding throughput, for sequential read, sequential write, and random read, so both of these three, we could achieve a effective speed up of n minus 1 times either S or R, right? Or R, right? So this is because we have a total number of n minus 1, these many disks that are solely used for storing data effectively. So in order to sustain this sequential read and write, and also this sequential random read, we can effectively use this first n minus 1, these many hard disk drives. Regarding random write, well, so here we're looking at a completely different story. And here the random write performance is R divided by 2. Why is that? It's because we have this single bottleneck that lies at the the parity disk. So if you take a look at this example as shown in this next slide. So let's say we have this random write that are hitting on logical block 4 and 13, even though these two can happen simultaneously. Right? Concurrently, but both of these two effectively get serialized over here because we have a single parity disk. So in order to update this logical block number 4, you have to first read this parity 1 first. So we have a small, so this is essentially a small write problem. In order to update this parity disk, you need to first do a small read to verify this parity value, followed by a small write. And then next, you need to handle this updates on the next logical block, which is block number 13 that is stored on disk number 1. So here, in order to update this parity 3 for logical block 13, you need to perform a first small read to just verify this small random small, verify this parity, and then followed by a small write to just update this value. But these two, this read and write, together with this read and write, they get effectively serialized because this is only a single disk, meaning this is a single bottleneck. So that is why for each and every one of these random write, it gets effectively translated into two small IOs. So that is why we have a decreasing factor of 2 over here. So that is why we're essentially looking at R divided by 2, because we have this parity disk bottleneck, and we have this small write problem. Small write, which get effectively translated into a small read together with a small write. So this is the factor of 2 over here. Okay. So regarding latency, well, for read latency, it's effectively D, because you could just random read from anywhere from the first N minus 1 disk that is used to store the data chunks. And for random write, this is 2D. Why is that? Because of same rationale over here. Random write. Because one single logical write gets translated, one single logical write gets translated to physical IOs. So that is why we're essentially looking at 2 times D. Okay. All right, so the last configuration, which is RAID number 5. Over here, so RAID number 5 is more or less the same as RAID number 4, but with one more metric, one more trick. So instead, it kind of rotates the parity data across all the involved, all the configured hard disk drives. So let's take a look at this specific example. In this example, we have a total number of 5 disks. Instead of designating one single disk just for storing the parity chunk, we kind of spread this parity data across all these 5 disks employed by RAID number 5. As shown in this example, so it's kind of rotating, right? So for the first strike number 0, its parity data is stored at disk 4. And for the next strike number 1, its parity data is rotating. Its parity chunk is effectively stored by its neighbor disk, which is disk 3, and the same for the next chunk, the next stripe. So this part is effectively used to store the parity data. And the parity data, the parity chunk gets effectively spread across this total number of 5 disks. Okay, So in theory, RAID 5 works almost exactly the same. It behaves almost exactly the same as RAID 4, except that it kind of rotates the parity block across the drives with slightly better advanced um, improvement in terms of various different metrics, as well shown in this next slide when we are talking about the theoretical analysis of RAID 5. Again, the capacity. The capacity is exactly the same as RAID 4 because in theory, it effectively uses 1/nth of the aggregated capacity for storing parity, right? So this is why we have n minus 1 times C. And also, effectively, it can only tolerate one single disk failure because, let's pick this, the middle stripe number 2 over here. So this is a parity data, and it can only tolerate at most one single disk failure. Let's say disk 1 failed, so this 11 gets lost. And you could do this exclusive OR by applying the rest 4 to get the result of this lost data, which is 11. But if for the worst case scenario, let's say both disk 0 and disk 1 get failed, there's no way that you simultaneously recover these two lost data because the rest 3 is not able to recover these two because it cannot just calculate the you lose more than one, right? Okay, so this is reliability. It can tolerate at most one single disk failure. For throughput, well, the first sequential read and sequential write exactly the same as RAID 4, which is n minus 1 times S. For this random read gets slightly better result, which is n times R. Why is that? Because, random read again, because you kind of rotate this parity block across all drives. So that also implicitly means that all the data, all the 5 involved employed hard disk drive could be used to effectively contribute to serve this data read operations. So that's why we have this scalability factor, the speed up factor of n. Like over here, let's again use the same example. So random read over here, we have all these 5 disks that could be effectively used to serve random read, right? So that's why we have n times R. Okay. For random write, what is the theoretical performance that could be achieved by random write? Well, if you take a look at this example, so here again, let's assume a random write that is hitting on disk 0, targeting logical block number 10, right? And let's assume, in order to fully serve this random write, you need to first do a read, to read this data out, and to try to compare it against the parity result, and then you perform, because you need to perform a comparison against this parity data. So basically that you get this 2 random read, right? First read the data out and then read the parity data out. And then you need to update this data block. You have a random write targeting this data block 10. And then, because you have to modify this parity result as well, right? So there's a fourth random IO, which is the second random write that is hitting on the second parity, which is P2, right? Which is corresponding with this logical block number 10. So that means a single random write gets effectively one single random write gets effectively translated into this 4 IOs, right? So let's assume at the same time some other random writes are hitting on some other data that are spread across the different set of disks. So in this example, instead of besides random write hitting on logical block 10, there's another random write hitting on this logical block 1. So this logical write results in a physical read of this logical block 1 and a physical read of this parity 0 to just verify the parity, and then followed by a random write to modify this data block 1 and another random write to modify this parity chunk. Because your original data gets updated, this update has to be reflected at this parity data. So that is why you have this random write targeting this parity data. So at the same time, a logic random write hitting on this logical block 1 gets effectively translated into this 4 IOs, targeting both its original. So as you can see, as part of this performance reasoning, so for a very large number of concurrent random read and write requests, right? Read 5 will be able to keep all the disk busy, right? So this is why we effectively see this n times r. But this n times r has to come with a decreasing factor because each random write gets effectively, as have already been shown in the previous example, in this current example shown in this slide, each random IO, each logical IO gets effectively translated into this 4 physical IO. So that's why we have this n times r divided by 4 as this random write performance analysis, right? Okay, so regarding latency, again, for read latency, it is D, and for write, this is 2D, because if you take a look at this for each random read, for each random write targeting a single logical block, it gets effectively translated into 2 IOs, which take place serially, sequentially. So that is why we have this an increasing factor of 2 over here for random write. All right. Okay, so that kind of finishes the RAID topic. So the last 2 slides basically summarizes all these inherent RAID properties in terms of theoretical analysis, covering all the interested metrics, including performance metric, capacity, as well as reliability. Okay, and last but not least, I do ask you guys to go through the textbook chapter, which has already been posted on the course website, in order to gain a more comprehensive and deeper understanding of this very theoretical analysis covered in lecture, right? Because the textbook does a really good job illustrating these various different examples and the reasoning behind these theoretical analysis. Okay? All right. Thanks.